Right, Algebra 2. So we are doing day 50 Edpuzzle. And what we're going to talk about today is simplifying radicals. Okay, and they can be radicals with root 2 or radicals. We're going to get them a little more complicated this year. Radicals with a 4, radicals with the 3, a root 3 or a root 4th root. Okay, so we're going to simplify radicals today, and we're going to do a little bit of multiplication with how do we multiply radicals together? All right, so when we're looking at a radical, just a little dissection here, we see that this right there is a radical sign. That's just the radical sign. Radical sign, which means what you've got here is a variable or a term raised to a fraction. Okay, let's not forget what radicals are. Okay, so radicals have fraction exponents. That is what they are. Fraction exponents, okay? But this number right here is called the index. We sometimes also call it the root, like the square root or the cubic root, the cube root. Okay, it tells us which kind of I'll tell you what it tells. It's actually the denominator of the fraction. This number under the radical sign has a name, and it's called the radicand. Okay, so we've got a radical sign, tells me I have a fraction exponent. We have an index or a root, the n, and we have the radicand. Now this radical can be written, this is called radical form. Okay, so we call this radical form. But we can write this as a, let's just say a was raised to its power underneath the radical. If there's a power underneath the radical, and if there is no power, no number there, it's a 1, right? It's implied because every number, just the number 3, is really 3 to the first power. So when you see a radical, you know you have a to this power, m, and then n, whatever is the root, the index, is in the denominator. These are the same thing, okay? And this is called the rational form. Okay, you see it has a ratio, right? It's a term to a ratio. Okay. Now let's get to simplifying radicals. And let's remember what's going on here. Just going back to a very simple square root of 9. You guys all know that that's 3, right? But let's just think about it for a minute. When there's no number there, we know it's the square, right? There's a little 2. The index is 2. And it's really asking you what number, when multiplied by itself this many times, 2 times, will give you 9. And you guys know that, let's keep it under the radical. If I were to multiply, keep the hat on here, 3 times 3, those are factors of 9. That would be, and radical times itself would be 3. Okay, and we can skip this step. We know that the square root of 9 is 3 because 3 multiplied by itself gives me 9. Twice. Multiplied by itself twice gives me 9. Okay, so how do we simplify radicals? Well, the way we do it, I'm going to show you 2 ways. The way that I prefer to do it is I look at this. I'm looking for square roots. So I have a list in my mind, right? And I'm seeing here perfect square roots, okay? Square roots. And it means like 1 times 1 is 1, 2 times 2 is 4. You guys know these, right? So these perfect square roots. And I ask myself, keep the hat on, right? Is there any a factor that multiplies to 108 that is a perfect square root? And I know that 3 times 36, I just factor that. I haven't taken any hats off yet. That multiplies to 108. That is a perfect square root. So the square root of 36 is 6. 6 times itself twice is 36. So this becomes 6 radical 3. And notice they're just multiplied together there. All right, 75. You say to yourself, okay, is there any factor, keep your hat on, of 75 that is itself, look, perfect square? Yes, 25 is a factor of 75. 3 times 25 factors. This is a perfect square, so this answer is 5 radical 3. Okay, basic square root simplification. There's another method called a factor tree method, and sometimes this really helps people. And the factor tree method uses prime factorization. It means take a number and break it down all the way till it's prime factorizations. So I look at 12. I'm not worried about radicals anymore. I'm just saying, what is 12? Well, the factors of 12, a prime factor is a number, by the way, that is only multiplied by, can only be divided by itself or 1. So 12, 2 times 6. That's prime, so we circle it when we make factor trees. 6, can 6 be broken up? Yes. 2, that's prime, times 3, that's prime, right? The only thing that you can divide 3 by is 1 or 3. So now I've got my, I've done my prime factorization. This is a square root. So I look at all my primes and I say, are there any pairs? And yes, we have a pair of 2s. So what that's going to do is pull out 2 outside the radical, but there's a 3, but it's not, there's no pair. So it has to stay under the square root. Okay. Now, if we did radical 12 the other way that I did up here, we would say, okay, what are the factors of 12? Is there a factor of 12 that is a perfect square? Yes, 4. So 3 times 4. I can take that perfect square root, so it's 2 radical 3. So you see, you get to the same place either way you like. Okay, 108. We already know what the answer is. Let's do it with prime factorization. I take 108 and I divide it by 2. 2 times 54, right? Divide, that's prime. I can still divide that. That's going to be 2 times 27. There's a prime factorization, 27. 3 times 9. There's a prime. 9 can be broken up into 3 times 3. I've made my factor tree. Now I find, this is a square root, so I find pairs, right? There is a pair of 3s. So a 3 can come outside of the radical. And then there's another pair here of 2s. So 2 multiply 3 times 2 comes outside the radical. And the only thing left is 1, 3. And then this 3 times 2, 6 radical 3. And we see we got there doing this both ways. You can get there. So whatever feels more natural to you, you go ahead and do that. I'm going to turn the light on. All right, 75. You already got, go ahead and try that. 75. Do a factor tree. Stop the tape for a second. Do the factor tree. Now 5, and I'm doing my factor tree, 5 is a prime factor. There's nothing that's divisible by 5, and that is a pair. So I can take that outside the radical. That doesn't have a pair, so it stays under the radical. And we see that either way we did it, we got the same answer. How did you do? Okay, let's talk about simplifying what we call other radicals. And by other radicals, I mean, we're moving beyond square roots. We see the cube root of 16, okay? And when you, let's just think about a cube root, just over to the side here. We know that the cube root of 27 is 3. We might know that. And what that means is 3, when multiplied by itself 3 times, gives me 27. We know that the cube root of 8, what is that? Well, 2 times 2 times 2, 2 multiplied by itself this many times gives me 8. Okay? So we have a little in our minds lists, cube roots. These are perfect cubes. The cube root of 8 is 2. The cube root of 27 is 3. The cube root of 64 is 4. The cube root of 125 is 5. Okay, so these are kind of like, we don't usually use many more perfect cubes than that. So when I look at this method, I think just like I did here, I identify the largest factor that is a perfect square. Here, I'm identifying the largest perfect root, right? It's not a square root, but I'm doing a cube. So I look at my cube list and I say, is 16 divisible by any of these perfect cubes? Yes. So what I do, just the same thing I did before, keep the hat on, right? Cube, just keep the hats on. Just factor it, 2 times 8. Now this, we can take it out because 2 times 2 times 2 is 8. So we take that outside of the radical and we get 2 cube root of 2. So that is a simplified cube root, okay? All right, let's look at this one. Now this is a fourth root of 32. So I make a list. I have a list in my mind of fourth roots. 1 times 1 times 1 times 1 is 1. 2 times 2 times 2 times 2 is 16. Okay, and really what it is 3 to the fourth power, 2 to the fourth power, 1 to the fourth power, right? Then this would be 4 to the fourth power and 5 to the fourth power. That's where I'm getting these perfect quartic fourth roots. Okay, so I look at this problem and I say, are there any quartic roots, fourth roots, that are factors of 32? And yes. So I keep my hat on. The fourth root, 2, fourth root, I'm still multiplying, 16. I'm just factoring. Now I'm taking this. The fourth root of 16 is 2. But this I can't take out, so it's just 2 times the fourth root of 2. That is a simplified fourth root. All right, this is another cube root. So I'm looking, 54. What factors of 54? Is 54 divisible by 1, 8, 27? I mean, there's not much really, right? So it's 27. So we know that this can be factored, right, into 3, I think. And I say that, all of a sudden I'm like, what? 54 divided by 3 is 18. So it's not 3. 54. Let's see, is that divisible by 8? I don't think so. 54 by 8. Nope. So this is how I figure out if I can simplify this. I take the number, 54, and I divide it by all these perfect roots. 54 divided by 8. Is it? Nope. 54 divided by 27. Yeah, 2. 27 times 2. All right, so 2 times 27. Getting tired here. All right, so we know that is a perfect cube. So that is just 3 times the cube root of 2. That is a simplified cube. Okay? All right, we're taking it up a notch here this year. All right, let's flip and talk about simplifying expressions when we have variables, okay? Because we don't just have numbers under the radical. How do we do variables? So this is what I want you to think of. You're factoring. Now, I'm not going to keep writing the square root multiple times. I'm just going to, let's just think about it this way. I'm going to take x to the 5th. And I know, let me just say this. I know that the square root of x squared, right? What number, what variable, when multiplied by itself twice, gives me x squared? Well, watch this. Square root x. Well, it's x that when multiplied by itself twice gives me x squared. See that? Okay. So I pull out, I separate this into x squared times x to the first. and this is a square. The index here is 2. So the square root of x squared is x. I can take it out. The square root of x squared is x. I can take it out. Now I can't, this is not large enough. So I have to leave that under the radical. And so when I simplify this, x to the 5th is really x squared square root of x. Okay, that is simplified with variables. Let's do it again. All right, this index is 2. So what I'm going to do is I'm going to break down this into factors that I know I can pull out. And so I've got the square root 25 times p squared times p squared times p squared. It has to add to 7, right? Because when I multiply these, I multiply to the first, okay? I can take all of these out, right? And that, so let's do one thing at a time. So first of all, we can do the number. What is the square root of 25? Well, I can pull that out because it's 5. I can pull out 1p, 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 which would be p, p, p. I cannot pull that out, right? I can't, the square root, I can't take that. So that has to stay under the radical. And so the answer is 5p squared radical p. Now I want you to see something. One of the ways we can do this, oh, this is cubed, right? This is cubed. One way we can do this faster is we can take p to the 7th. What p to the 7th divided by 2, okay? So 2 goes into 7 3 times with a remainder of 1, okay? So I know that that's going to be p cubed. I can take 3 p's out and 1 will be left over. That's another way to think of simplifying variables. Let's take some practice. Let's keep going. Okay, looking at another problem. Let's see if I can zoom in a little bit because these are hard to see, maybe. Oh, you're looking at your paper. So we've got the square root. We're going to break this up into factors that we know we can pull out. And so we've got the square root of 8 x to the 5th. Well, let's just think about it. And I should have done that 8. The x to the 5th, let's take 5 divided by 2. What do we get? We get 2 goes into 5 twice with a remainder of 1. Okay, so I can take out 2 x's, but I have to leave 1 x inside the radical because I only can take out 2 x's. And then I've got z to the 8th. Well, I take 8 and divide it by the index, and that's a 4 with no remainder, so I can take out z to the 4th outside the radical, and I've only got x left. Now, what about this 8? Well, I can break up 8 into 4 times 2, and 4 is on my perfect square list. The square root of 4 is 2. I can take it out because you can take the square root of 4. You can't take the square root of 2, so you have to leave that under the radical. So this would be the simplified form of that. Let's keep going. All right, y. This is the cube root of y to the 6th. Well, you just take y. You take 6. You divide it by the index, which is 3, and you get 2. So you can take out 2 y's. So this is really y squared. And we know it is y squared because look, if this is just a fraction exponent, let's turn it from radical form to rational form. It's really y, put the 6 in the numerator, put this term out, the root in the denominator, and isn't that y squared? Okay. All right, looking at this one. The cube root, I know the cube root of 27 is 3. I can take that out. Now, this is really x to the 5/3, isn't it? X to the 5/3. Well, 5 divided by 3 is 1. If I divide 5 by 3, I get 1 remainder 2. So I can take out 1x, but I have to leave under the cube root sign 2 x's, x squared. All right, I'm going to give a color just so we can see the cube root of y cubed. This is y to the 2/3. Well, I can't divide anything out. This is not larger than this. Therefore, the y squared has to stay under the cube root sign. Okay? It can't come out. All right, last one. The fourth root of 243, a to the 7th. Well, I look at my fourth root, my perfect fourth roots, and I say, is any of these a factor of 243? And I don't know. I could start dividing. Okay, so batteries are low. Sorry. So I take 243 and I divide it by 16. Is that divisible? No. I take 243. I say, is it divisible by 81? Whoops, I didn't do that. 243 divided by 81. And I get 3. Yes. Okay. So I can take the fourth root and break it up into 3 times 81. And I can't take the fourth root of 3, but I can take the fourth root of 81. That is 3. So that can come out. 3 can come out. But under the fourth root, I have to leave the 3. Now, what about this a to the 7th? Let's think of it. A to the 7/4. Okay, well, at least one a can come out. 7 divided by 4 is 1 remainder 3. So 1a can come out. But 3 a's, a cubed, have to remain under that fourth root sign. Okay, so that's simplifying with variables. Okay. Now, let's do a little bit of multiplying to finish ourselves off. So, when you're multiplying radicals, we'll do addition later, next class or two. All right, when you're multiplying radicals together, you can only multiply radicals by using the product rule. Oh, let's remember what the product rule is. The product rule says x to the n times x to the m, right, is x to the n plus m. You know, if you have x squared times x to the 7th, that equals not x to the 14th, right? It's x to the 9th. Okay, so that's the product rule. But you can only multiply radicals using the product rule when the radicand is the same. When the radicand is the same. Okay, then you can add the exponents and solve it that way, simplify it that way. When the index of 2, like here, square, square, cube, cube, when the index is the same, you can multiply the radicands under that index. Okay? All right, so let's look at this. We have the index is the same, so I can say that is equal to the square root of 5 times the square root of 35, which doesn't help me because that's not, it's a little bit simpler, but that's all I can do. Now, I've got the cube root. Well, their index is the same, so that's equal to the cube root of 36. Now, if I want to think about simplifying, I have to look at my cube roots and say, is 36 divisible by 1, 8, or 27? No, so I can't simplify anymore, but sometimes you can simplify further. Sorry. All right, this one. The index is both 2, so I can say that's equal to the square root of 10 times 5, 50, y times y, y squared, z, there we go. So I can do that. Now I have to ask myself, now that I've multiplied it together, can anything come out? And the answer is yes. 50 can be factored right, into 2 times 25. And the square root of 25 is, from here, the 5 can come out. Well, the 2 would have to stay underneath the square root sign. But then the y squared, right, is, if you think about y, it's y to the 2 over 2, to the 2 over 2. Well, that is just y, and it can come out. Okay, so this would be y squared, and that can come out as y. And then z is really z to the 1/2. Okay, when the numerator is less than the denominator, you can't do anything. You just leave it under the radical sign. All right, let's go to the next one. So here we go. They're both cubed, and so therefore we can multiply what's under those radical signs together. So that's the cube root. Now let's multiply. 6 times 12, 72. A cubed times a to the 4th is a to the, add those together, 7th. B squared times b is b to the 3rd. And now we ask ourselves, can we pull anything out for these cube roots? Well, cube roots. I look at my cube root and say, is 72 divisible by anything? Yes, 72 is divisible by 8. So I can say that this breaks down into the cube root of 8 times 9. And then a to the 7th is really a cubed, right? That would add up to 7. And I could take out 2 a's because the cube root of a cubed is a, the cube root of a cubed is a. So, and then here, b cubed, I can just take out. So I can take that out. I can take the cube root of 8. So when I simplify this, the cube root of 8 is 2. It can come out. I can't take the cube root of 9. There's nothing when multiplied by itself 3 times gives me 9. All right. So the 9 has to stay under the cube root sign. I can take out 2 a's, a squared. I can take out 1b, and 1a is left under the cube root sign. All right, so keep going. So they're both 6th roots. So I can multiply everything under that 6th root. 10 times 5 is 50. M to the 4th times n to the 9th is m to the 13th. And then I say the 6th root of 50. Is there anything multiplied by itself 6 times gives me 50? Not that I know of. So 2 doesn't, so it won't be anything else. So 50, they can't simplify that. Remember, it's m to the 13 sixth. 6th goes into 13 twice, so I can take out 2 m's. 6 goes to 13 twice, remainder 1. So 1 m has to stay. So m squared times the 6th root of 50 m. That's as simple as we can get right there. All right, so looking at 4th, okay, here we go. We've got 2 different indexes. The index is different, so I cannot just multiply 2 times 2 because the index is not the same. But what I can do, because the radicand is the same, when the index is the same, you could multiply radicands under that index, but you can only multiply radicals using the product rule when the radicand is the same. So I can use the product rule. I'm going to do that. So let's write it in its rational form. 2 to the 1/4 times 2 to the 1/5. The radicands are the same, so I can add. So this will become 2 to something. It's going to be 2 to the 1/4 plus 1/5. I have to do that math, right? So off to the side or whatever, I say, okay, what is 1/4 plus 1/5? Well, I need to get common denominators. 4 times 5 is 20. So this will be 5. 1 times 5 is 5/20. 5 times 4 is 20, so this becomes a 4. And I get my common denominator, and then I 5 plus 4 is 9/20. So this times this is 2 to the 9/20. So I can multiply those radicals together because the radicand is the same. I can use the product rule. All right, a lot of stuff going on here, a lot of details, but practice will get you there. All right, I'll see you in class.